Okay, hello everyone. Thank you and welcome back. So previously we talked about some exciting topics in LMMs, grounding, as well as the agent systems. So for the remaining part of the session, we will shift the topic a little bit onto more about the generative foundation models that are a series of models that can create visual content such as image, video, 3D, and so on. So in my sharing, I will be mostly still focusing on the image generative foundation models, and Kevin will later talk about video 3D and other exciting topics. So starting with a very brief outline for today's sessions. So we will still mostly focusing on the recent advances and techniques in how to train a better generative foundation models. So we see an empty wind graph here, which we will later fill in different contents. For example, the advances in data architecture training paradigm, as well as some other specialized topics. For example, how to speed up the diffusion inference, how to do the post-training for human alignments, and so on. And after this first part, we will assume that we know the technique about how to train an effective image generative foundation models. So what can we use it for? Intuitively, we have a model that can generate images, and we have various applications that needs generated images, so we can directly use them for such applications. This leads to the problem of how do we properly evaluate and compare different models so that we select the best one that fits our need. As we will detail later, this turns out to be not as simple as we might expect it. And also, we are interested in the applications or scenarios beyond the simple image and video generations. We are curious that if, when combined with LMMs and other effective understanding systems, whether such combinations leads to a stronger intelligence. So we start with the first part about the recent advances in training techniques. So we actually have this same tutorial with the same image generation related topics in the last year's CVPR. So one natural question is, compared with the last year, what's new or what are the recent advances? So we would like to, so one thing good about visual generation is that the results, basically the generated images, are more easily for humans to visually compare with. So in the bottom right are the results from one of the top performing model from last year, Stable Diffusion XL, in comparison to the right side that are with the same prompt, but with one more recent model, DAI3, as well as its variants, we can clearly see the significant improvement in the generated image qualities. More specifically, this involves better quality. So for example, if we look at the middle CVPR poster here, now, for example, on the syntax, it can more reliably generating the correct syntax. For example, not only spelling this CVPR correct, but if you further zoom in the bottom, there are the correct spelling of computer vision and pattern recognition, June 2024, which seems to be quite a challenge or even hard to imagine in the last year. And also, it in general better aligns with the human intention. So here it means in general, by giving a generated images, it is more likely what we humans would prefer. This might jointly reflected as better aesthetic, better prompt following, less harmful content, and so on. And other than the quality improvement, there has also been significant improvements in the inference and the model computation cost. For example, the effective speed up method allows us to reduce the required iterations for generating an image from, for example, 50 to even 1 step. So one may naturally wonder what are the actual technique improvements that to achieve all of those exciting quality improvements. So before actually diving into these recent advances, we still wish to start with a very brief but basic overview for the image generation techniques. So here we highlight a few representative text-to-image generation techniques. So starting from the top left is the generative adversarial network GAN. So GAN involves a pair of generator and discriminator. The generator generates image from noise conditioned on certain condition signal, for example, the text prompt, and produce the image that we actually want. and the discriminator compete against it to distinguish whether this generated image is real or fake, where fake means produced by the generator and real means, for example, following a real natural images. Also recently, the idea of this adversarial training, actually, people show that it combines quite well with the diffusion model as a way to speed up the diffusion method, also known as the diffusion distillation. We will zoom into that part later. Next onto the top right is the autoregressive generation approach. So the core idea is to involve a set of tokenizer and a detokenizer, where this tokenizer converts the image into a set of discrete tokens, and which are then used for example, transformer-based architecture to predict them token by token following a specific order. For example, one typical order is just scan row by row from top to bottom. And these predicted tokens are then sent to the VQ-GAN decoder to bring back the actual image prediction. And we also have the non-autoregressive approach, where the core idea is that instead of generating one token at a time with a transformer, in each decoding step, we can in parallel generating multiple token predictions so that the image generation can be speed up. And finally, in the bottom right is the diffusion process, which involves a stochastic differentiable equation to gradually involve one sample from the noise distribution into a sample that falls inside the real image distribution. So the denoising network is trained to predict a small amount of noise to remove from the image in each step, so that after certain iterations, it involves a initial noise into a reasonable image. So further zoom in a little bit into the diffusion part. Here we use latent diffusion model as an example to continue our basics overview, as latent diffusion model is now one of the representative approach for image generation. So the core idea is that instead of doing the diffusion directly in the image pixel space, we can first map the image into a latent space that is usually of a lower dimension and perform diffusion denoising actually on that latent space, so that we can save some compute. So a representative architecture of the latent diffusion model is shown on the right, which mainly involves three parts. So in the leftmost is a pair of encoder and decoder from the variational autoencoder or VAE. So what VAE does basically is with an image sampled from the image distribution, we can map it to a corresponding sample of the latent sampled from the latent distribution. So as we mentioned earlier, this latent distribution is actually where the denoising conducts. And the second part is the rightmost, which is a conditional encoder. So specifically, if it is a text-to-image generation, the condition is a text caption, and the corresponding encoder is thereby a text encoder. Earlier studies usually involve a single clip text encoders, whereas more recent studies showed effectiveness of including additional text encoders, for example, T5, and in many cases combined with additional clip text encoders. And finally, in the middle is the main part of the diffusion denoising part that performs the conditional denoising unit. So this conditional unit contains a series of upsampling, downsampling, and upsampling blocks that gradually fuse the condition into the main visual stream that is our latent, and predict the amount of noise or its equivalent variations to remove in each step, so that when at inference, when we run this denoising iteratively, we can gradually remove the noise from the image and end up with a high quality image. So due to the limited of time, I will stop here for our very short and brief review for the text-to-image basics. There has been some really great tutorials in CVPR and related conferences, so you are more than welcome to check those for additional details. So back to the CVPR poster examples we have just seen, and again now when compared with the last year, seems that the image quality from this example is significantly improved. So we next try to select a few highlights from the representative models from last year, such as DALL-E 3, Stable Diffusion 3, Midjourney, PixArt, VAR, and so on, and organize their key claims and contributions from the following three perspectives. That is the data, architecture, and the training paradigm. So we start with the data part. So we have already know that in order to train good image generation models, we need good image data, and people have been working hard to collect a large amount of high quality image data. And as shown in DALL-E 3, as well as some other related research work, it is also equally important to have the high quality of the caption, that is the text, paired with this image used to train the model. So we need not only clean, so that we need of the importance that we need the clean and the descriptive caption to train the text-to-image generation models. So let's first recall like how previously like this such text-to-image generation, or as well as its counterparts, the image-to-text caption models are trained. So training such model usually involves getting web croned data. So on the web, we can find abundant amount of images, whereas the corresponding text description paired with it, instead of a long and descriptive captions, are usually the alt text shown in the first row. So this kind of alt text in many cases are not in proper grammar, and even and of short text length, and even worse, sometimes it's just not visually correspond to the image's semantics. For example, if we look at the leftmost, the best type example, the corresponding alt text is that this specific best type is now available at a specific website, which actually almost does not relate to the visual content in the image. So in DALL-E 3, they show the importance of recaption. So recaption mainly it can be break down into two aspects. So one thing is that with the long and descriptive captions, the caption always strictly describe the visual content appears in the image, so that it becomes less noisy, that there won't be those kind of alt text noise that basically does not talk about the image content. And also, they show the importance of having actual long captions that tries to cover all visual details that appears in the image, instead of as shown in the second row, that is of a shorter caption of around 10 words that people use to generate the image captioning for. So by scaling up such recaption data with long and descriptive captions, it actually significantly improved the prompt following capability, which is one of the known challenge for the text-to-image generation model. So the right side two examples illustrates the two sub-problems under the prompt following. So the upper one, a horse riding astronauts, is known to be a challenge case that when we try to generate an uncommon thing, that the model might, in many cases, just follow the prior of its visual thing, that it will usually generate an astronaut riding a horse and vice versa. And with the clean image captionings, the T2I model tends to know that it should always strictly follow the prompt, and in this case, improve the prompt following in this scenario. And the bottom example, a woman stands wearing a black and white coat over a dark vest, orange shirt, and pink tie, indicating the challenge that sometimes when we generate a prompt with a lot of details, the model might overlook some of them and choose to hallucinate some other generations. And with the long descriptive captions, it also significantly improves the prompt following in these scenarios. So that's the data on the importance of recaptioning. Next, we move on to the architecture. So one highlight of the architecture is the success of fully transformer architecture, represented by the DIT work titled Scaling Diffusion Model with Transformers. So recall when we introduced the latent diffusion models, we mentioned that the earlier standard practice is involving a conditional UNet to do the denoising. So further zooming into this UNet, within each downsampling or upsampling block, it contains a cross-attention layer for the image text fusion, as well as a convolutional layer to propagate or refine the features. So in the DIT architecture, in order to achieve a fully transformer architecture, we can just replace this convolution with a self-attention layer. And the study also explores other effective ways to do the image text fusion. For example, they observed that project the text condition into a set of modulation parameter turns out to be quite effective, as shown in this specific DIT block. And also, importantly, in the paper, they have an extended discussion on the model's scaling behavior that if we further increase the model capacity and reduce the patch size, the performance can be consistently improved. So during the past year, this effective scaling behavior has been validated by quite a lot of exciting, more recent models. This include on the image side, it picks out the Stable Diffusion 3, and on the video side, the Sora model are all based on such fully transformer based architecture. And next, moving on to the training paradigm. So let's first talk about on the diffusion side. So on the diffusion side, or more broadly, the iterative generation side, there has already been some good works on how to further improve the diffusion training objective. This involves a better scheduling as well as in each step, the proper target to predict for the network. And many of them consistently lead to better performance and have been incorporated in the more recent or more modern diffusion model training. And here we wish to also highlight one emergent technique that is using the flow matching to train such models. So image generation can be viewed as solving a mapping between two distributions, where the starting one is a noise distribution, for example, commonly a Gaussian, but we can also take other noise distribution into the real image distribution that we actually try to generate. So if we can solve this problem, we can generate images simply by sampling different data points in the noise distribution and map them somehow into our real image distribution. So giving a starting point from the noise distribution, we can keep the shown in the center. This is basically a velocity field. You can interpret it as at each step, this velocity field gives us the signal about which direction we should go to and how fast or how far we should go to. So if we know this, we can simply use the upper differential equation to gradually add signals into this initially sampled noise point and finally end up with the left image that we try to generate. So the core idea of flow matching is that instead of directly generating or predicting the final real image distribution we try to generate, if we can somehow just perfectly mimic this velocity field, we can just sample from noise and gradually following this differential equation and get arbitrary number of images as we want. So this is indicated as in this training losses. So here, this theta is basically a neural network that we try to train, and the output of this neural network will be the a similar mimic velocity field indicated by this v theta here. So as shown in this loss, we want it to be as close as possible to the real v so that we can just replicate this velocity field. So one simple but effective way of defining this v is just a constant speed and a straight flow between the noise and the image distribution. That is the vt equals x1 minus x0 here. And we have all the pieces we need, and then we can just have multiple training samples. That is our xt. By having each training sample, we can mimic all the intermediate steps about how it flows from noise to image and use such signal to actually train a flow matching model. So we quickly talk about the improvement in data architecture and the training paradigm. Next is one nice case study, the Stable Diffusion 3, which is one of the most capable open source generation models that contains the related advance that we have just talked about. On the data side, it uses CogVLM to do the recaption, and it also involves the T5 encoder to do the text encoding together with additional 2 clip text encoders. On the architecture side, it involves a fully transformer architecture based on DIT with some minor improvements that it keeps a separate stream of the text condition so that text can be fused into the image with both attention as well as the modulation. And for the training paradigm, it used the rectified flow objective that we have just shown in the previous page. And altogether, this leads to the nice generation result quoted directly from their report as shown in the bottom 2 figures. So that's the training paradigm highlights mostly on the diffusion side. So there has also been some exciting recent advances on the autoregressive generation side. So one highlight is that people start to also study carefully about the scaling behavior of the autoregressive generation. For example, in the LMMs work, where the qualitative results are shown in the top right. And also, instead of generating autoregressive as token by token as a spatial scan of the image, there has also been some exciting recent work showing the potential of doing the so-called next scale prediction, as illustrated in this bottom right figure. So the core idea is that instead of generating the next spatially adjacent tokens, we can define multiple resolution of this image and starting from the most blurry one, and in each next step, jointly predict all the tokens in the next or higher resolution version. And after k steps, it brings us a high quality images. That is our final generation result. So I have talked about relevant topics on how to train good generative foundation models. As a quick review, we talk about the data improvements about the importance of recaption architecture, that is the DIT, as well as the training paradigm of flow matching and the next scale prediction in autoregressive generation. So a natural next question is that, is this all about how we train a good generative foundation models? At least I would like to argue that this is still not the complete picture, or at least this somewhat focuses more on the pre-training side. That if we want to directly deploy such models, there are still several problems remaining. So next, I would like to highlight two of them, which I think have some quite significant improvements during the past few years. The last 1 year. So the first is about the slow inference speed problem. So more specifically related to the diffusion models, that we know that diffusion model in generation, we still need to do such iterations. And in practice, in general, such iteration is slow in speed, which potentially limits its applications in certain scenarios. And also there is the problem of so-called human alignment, and which we will zoom into later. So we first talk about the diffusion inference acceleration. So actually, one line of research towards this goal of speeding up the diffusion inference speed is the so-called advanced diffusion sampler, where the goal is to develop a more effective inference time sampler that can be applied to arbitrarily pre-trained diffusion models to speed up the inference speed, for example, from around the 50 step to the state of art of around the 10 to 20 steps. So there has been significant speed up, for example, around 3 to 5 times. But if we even target for a more aggressive step reduction, for example, thinking about even reduce it to less than 10 steps, we at least the existing models will observe that using such inference time sampler will lead to more severe performance degradations. So in today's session, we'll be focusing more onto another parallel direction that relax the condition a little bit, that now we allow certain amount of diffusion model training or distillation, and see if in that case, we can even reduce the step to like a much fewer or more extreme case. For example, the bottom left are the results, just running one-step diffusion with the pre-trained diffusion model frozen. So this will be the generation result. So in general, we can see it is very blurry, and in many cases, it's even hard to distinguish what we try to generate. In contrast to on the right side is the one-step generation result with the diffusion distillation from one of the recent papers. And as we can see, it can actually generate quite reasonable quality images. So next, we will talk about related works along the diffusion distillation work. So one pioneer work as well as representative work is the idea of consistency model, or specifically the consistency distillation as part of the consistency model paper. So the core idea is to introduce a new learning objective that maps all noisy image along any time of the diffusion process into its initial x0, that is the clean image state. So this is nicely illustrated in the left side figure, that we use the objective to try to map all the intermediate noisy image also to the original x0 state. So by implementing the idea of consistency model on one of the latent diffusion models, as shown on the right side result, quoted from the latent consistency model paper, we can see that the bottom right's one-step inference result, although somewhat still blurry compared with the 50-step result, are actually of much better quality compared with the naive one-step result we have shown in the previous page. So if we want to further improve the performance, we can simply add certain amount of noise to this initial one-step generation and further run multiple network inference. And it, for example, bring the upper four-step result are actually of better quality. Following the initial success of consistency models, there has also been some recent further improvements. For example, one core idea along this direction is the introduction of the sub-trajectory idea, that instead of mapping all points directly into the x0 state, we try to split the ODE trajectory into multiple segments, and it only enforces, for example, the later half of the points to map to the middle point and the other point to the x0. So the study showed that it can lead to better few-step results. And as we mentioned earlier at the very beginning, another idea turns out to be quite effective in diffusion distillation is the concept of adversarial training. So at a high level, the idea is that in addition to the generator that we try to sample image with, for example, one step from, whether we can also have a discriminator that paired against it and provides the valuable signal of whether this image is like blurry or not, or how to make the image more realistic. So in one of the early work, the UFO Gen, they adopt a pair of generator and a discriminator. So both models are initialized from a pre-trained stable diffusion. So the behavior of the generator mostly still follow the original diffusion training, that is continued training with the reconstruction loss. And the last output layer of the discriminator is replaced with a binary output. Then now instead of predict the latent or the image, it tries to simply give us a signal whether this place is real or fake. And this is jointly trained together, similar to the GAN training. And as shown on the right side result, it turns out to be quite effective that in the one-step generation result, it becomes much less blurry and of better image quality compared with the latent consistency model we have just introduced. And also, follow-up work also proposed other effective improvements on how to better design the discriminators. So, our previous discussion corresponding to this full pre-trained distillation, that we take the entire stable diffusion or other diffusion model pre-trained and only remove the last layer to output a binary label. And some studies show that it is helpful to, instead of doing the classification, real or fake classification in the latent space, we first use a decoder to bring it back into the real image, and directly in the pixel space, use a specific vision encoder, for example, Dino V2, to perform that real or fake classification, which seems to provide even better visual qualities. However, one problem intuitively is that now such approach involves a separate Dino encoder as well as a separate decoders. In general, it would make the computation much higher. And further improvements towards that, showing that we can actually just take the downsampling part of the diffusion model that take an image, or specifically take a generated latent, we map it into the bottleneck feature of a smaller spatial resolution and performs the classification on top of that bottleneck feature, which turns out work quite well and actually can also provide the very discriminative feedback signals. So that's on the discriminator. So that's mostly on the discriminator side about how can we design effective discriminators to do the diffusion distillation. And on the generator side, other than the reconstruction loss, there has also been some other effective losses and objectives that we can further improve. So, instead of doing the reconstruction loss, one effective idea is to design a certain way of the distillation loss. which usually will involve a teacher model. So the right side figure borrowed from the adversarial diffusion distillation paper nicely illustrates this. So if we look at the two images pointed by the arrow, so in the second row, this x theta hat is the student's generation. So basically, when we later do the inference, this is an actual image we get with one step. So the objective is simply to update the parameter theta of the student model so that this image can have better quality. So this is done by having another teacher model that is frozen. And we send the student model, we add a certain amount of noise to it and have the teacher to remove that noise we added. So that after this add noise and remove noise, so after this add noise and remove noise process, the output image from the teacher are in general of better quality compared with the one of the students. And we can simply apply a similarity metric to make the student's model as close to as this new teacher output as possible by updating the parameters of the student's model. So this is the high-level idea of the distillation loss. And furthermore, in addition to compute the diffusion loss on a specific student's output samples, studies like distribution matching distillation show the importance of matching the so-called distribution of the current student's model's output. So the idea of matching the student's distribution instead of one sample is implemented by having an additional diffusion network that is fine-tuned with the diffusion objective tuned purely to keep track of the student's generator's current output. So basically, this is done by having the students generate one or multiple new samples and fine-tune this teacher model, fine-tune this fake net from the original high quality into the one that more closer to the student's output. So later, when compute the loss, instead of computing the teacher model's output with the student's generated image, we now have the fake net generate another image that follows the student's distribution, but not that specific sample, and compute the pair of distillation loss on top of that. And it leads to a more, and in general, it leads to better distilling quality as well as somewhat improve the diversity. So that's about the end of the diffusion and inference acceleration part. So at the end, I would like to quote this nice figure from the DMD2 paper that compares different representative distilled diffusion models. So all of the left four columns to the teacher model, that is the stable diffusion XL shown in the right side. So if you look, if you compare the quality, although if you look really hard into some details, you can still find the students at fewer steps. The quality, some details are not as good as teacher, but in general, it is sort of comfortable to say that nowadays the student diffusion models can generate results comparable to the teacher model in very extremely limited time steps. Oh, sorry, inference steps. And also inspired by the success of image diffusion distillation, where recent work have also started to explore the way to do the distillation or for inference speed up for the video diffusion models. So the right side is the 4-step generation result from the motion consistency model, and the the left side is the 50-step teacher model. And we can see the quality is actually quite good also in the video domain. So back to this initial figure. After the pre-training, we talk about how to do the inference acceleration to solve the slow inference speed problem. Another problem we listed here in the bottom right is the so-called human alignment. So intuitively, after we pre-train the model with the with image text pair, it will try to best follow the pre-trained image distribution that we feed the model. So although it is important that we have high quality data and we try to make this initial training data image distribution as good as possible, one realistic is that the higher we set the bar for the data quality, the fewer samples we can get. And we all know having enough number of samples is also equally important to train a good model. So it would be really nice that after the pre-training, there exists some effective techniques that we can so-called just do a post-training stage that we slightly shift the distribution towards more towards the one that humans will in general prefer. So in last year's CVPR tutorial, we actually have a dedicated session focusing on how to do the human alignment for the text-to-image generation model, where we review related literatures from all those different perspectives. This year, thanks to the advancement in the post-training techniques, and many of them inspired by the large language model post-training, we can have some more unified solutions, which we will next talk about. So let's first have a very brief review about the related techniques in large language models, the human feedback learning. So on the left side is the very famous reinforcement learning from human feedback that involves the multiple stage of first collecting the preference data, and then use such preference data to fine-tune a specific reward model that later, when feed new samples, it can provide us with a reliable reward signal about how good is this sample, or for a pair of sample, which one is even better. And this reward sample is then used to tune a language model policy using the reinforcement learning that leads to a language model that better follows the human intention. And later, there are also work such as the direct prompt optimization, DPO, that tries to get rid of the reward model as well as the need for reinforcement learning, that it tries to directly use the preference data to tune the final language model. So the high-level idea is that with a pair of preference data, the probability of this preferred sample should be higher than one of the reference sample. And this is used as the training loss for the maximum likelihood training directly for the final language model. The development for the image generation post-training techniques are largely related or inspired by the techniques in LLMs. So next we will review according to these two dimensions of whether such technique involved with or without an explicit reward model, as well as whether it is tuned with a reinforcement learning or direct maximum likelihood training. So starting with the conceptually most similar to the ILH, yeah, that's the correct page. Starting from the work that conceptually most corresponding to the ILHF, that is, the approach involves a reward model that gives reward signals, which are then later used to update the diffusion model with reinforcement learning. Specifically, such works can view diffusion's iterative denoising process as a Markov decision process and define the state and action accordingly to update the diffusion network. So here, the choice of this specific reward function are actually quite flexible. It can either be a dedicated model that provides a specific reward signal along a certain dimension. For example, we want to have a higher compressibility, having better aesthetic or better image text alignment. It can also be a more general reward model tuned with the collected human preference data to simply try to best mimic the human preference, which when human users give such preference annotation, will usually jointly consider multiple aspects. And as a case study, we show one of the work here on using the diversity as reward. And also one highlight is that here we also show that the reward, the diversity reward or other reward can be computed by having users provide a set of reference images. For example, the right one shows the example of generating shocks. So if we directly sample from diffusion models, it will usually generate the shock view from the underwater. But for certain scenarios, the users might just also be interested from some images shot from above water or from a boat. So they can simply provide a set of images, and a diversity reward will try to match the distribution of this set of reference images and generate the final model outputs that contain both underwater and above water images. So again, I wish to highlight that it is quite interesting that now we can have a set of reference images to implicitly indicate the human preference, which can later also be used for the model customization. And next, instead of using the reinforcement learning to send back the signals from reward models to updated models, which there also exists some discussion on the potential of sampling efficiency, Draft directly backprops the gradient reward signal with regard to diffusion model in a few denoising steps. And the results are shown on the right side, which also improves the human preference. And the previous method all involves a reward model, and another line of research tries to copy the concept of direct prompt optimization in LMM into the diffusion models, with the shared core idea of directly having some paired preference data and try to have the probability when generating this preferred image to be higher than one when we sample this reference image, so that these laws can be directly used to fine-tune the diffusion model. And again, right side also shows its effectiveness in better align with the human aesthetic and other preference. So again, we talk about various topics on how to train good generative foundation models. We start about the pre-training stack, about data architecture and paradigm, and we also highlight some of the further improvements, such as how to do the inference acceleration and use post-training to do the human alignments. So now we can somewhat assume that we know how to train a good generative foundation models, and this might bring us a good, reasonable quality models. So what's next? So the first is about direct applications that we want to use it to generate images for us. So the related problem is how to do evaluation. And also, as mentioned earlier, we will also discuss in the next part the usage beyond generation. So we start with the image generation evaluation, which turns out to be actually harder than we expected. So just have a look at these bottom two images generated by two different model variants. So the prompt is using a descriptive prompt shown here, which might be a little bit too long, but the key concept is we try to generate a scene at the New York Times Square, celebrating the new year of 2024. And it also indicates on the right side screen, it should write Happy New Year with some other details. So you can take a second to think about like A or B, which one would you prefer? So when we think about like how to compare this, like in general of comparable quality images, but definitely not perfect images, first, it's quite obvious that the image level metric, for example, the FID and the clip score, will in general fail to give us a very clear signal, as most of them already captured of reasonable image aesthetic and also capture the key concepts such as New York Times Square 2024 and so on. So in order to do that, what we humans might do is first check the details. For example, on the left side image, there is a Statue of Liberty in the center of New York Times Square, which according to our world knowledge does not make sense. And also when we look closer into the syntax written on the screen, when trying to spell the Happy New Year, it lost one W letter in the new word. And there are also some problems for the right side image. For example, the girl's face shown on the digital screen is not of that high quality. And also the previous illustration just mentioned various diverse aspects, for example, syntax, the world knowledge, and many other aspects that we need to consider in order to do the generation evaluation. And finally, another challenge is that the models continuously getting better and it now can do new things. So for those emergent scenarios, we also need new benchmarks. So to my knowledge, most of these challenges haven't been fully solved, but I would wish to next highlight some of the related works that tries to push along each of the directions. So the first is the check details. Again, we mentioned Statue of Liberty, the syntax spelling, and many other aspects. So in T2ICOM bench, they show that we can use separate models to dedicate it to check each aspect. For example, we can use the VQA model to check whether the object attributes are correct and use a detection model to check whether the object spatial are correct. And similarly, in the Gen eval, where the framework show in the top right, it has a pipeline to check the object presence, count, position, attributes, and so on. And as we mentioned earlier, another challenge is that there exist so many different aspects to check, and it would we can imagine that it will be quite complicated if we have an evaluation pipeline containing 10 or 20 different modules, each with dedicated models. So luckily, given the power of the large multimodal models, it has the potential to be repurposed into an evaluator focusing on checking a specific aspects by simply changing the prompts without changing the actual model weights. So the right side is the prompt directly quoted from the DAI3 paper that they repurposed the GPT-4b model in order to evaluate the generated result from the DAI3 model. And the problem becomes even more challenging when we extend the input and output modality to multimodal inputs and outputs. So the left is one pioneer work named OpenLeaf that tries to evaluate the generation in such scenarios. It defines a various complicated perspective. For example, the image text alignment in the input and output, the character consistency, and so on. And luckily, we can simply have a different prompt, but using the same model of GPT-4b to solve the evaluation all at once. And finally, there exist so many, and finally, the generation models are getting better and better. For example, the right three are from the DAI3 and the design bench paper that, for example, we mentioned in the very beginning. Now it can spell even those tiny fronts of computer vision and pattern recognition in June 2024 quite well. This enables the new scenarios such as visual design, like we want to put some tiny word or art design on a perfume bottle, or design a book cover for the Seattle Symphony, and so on. So in this work, they comprehensively, from the perspective of the visual design, design different evaluation categories as well as prompts corresponding to the application scenarios and the techniques used for those emergent scenarios. And also extending from image text to image generation into the multimodal input and output is another emergent new capabilities. And we need to think closer about if there exist such models, what it could enable, like what are the high value applications, and for them, what benchmarks should we develop? For example, here in OpenLeaf, it shows that it's quite helpful for generate story, instruction videos, and so on. So I have talked about evaluation, and again, imagine the high-level picture. We first talk about how to train the model, and after we have the model, we can directly use them for certain applications that requires the evaluation. And the next part, we're also curious whether the proper training of such generative foundation models can actually lead to our ultimate goal of achieving stronger intelligence. And I wish to discuss this as well as its combination with large multimodal models, which at least to this point, mostly focusing on the understanding part. So I wish to chat about the related topics, mainly from these three directions. So the first is mostly still from large multimodal models to benefit the generative foundation models, that how we use LMMs to do the reasoning and help better generation. And the second part, try to position these two parts in an equal position about if we can have a unified system, whether it can mutually benefit each other and leads to a better model. And finally, the opposite direction, that if we have good generative foundation models, whether we can repurpose it or extract feature from it to help the diffusion, to help the understanding tasks. Also, we know that these related topics are highly relevant to the successful exploration of generating synthesized data for training, but in today's session, we won't cover related topics. So we start with LMMs help generation reasoning. So one most intuitive motivation is that LMMs contain those different world knowledge. For example, the previous Statue of Liberty in New York Times Square example. And the study showed that it can help better prompt the user's input prompt. For example, if users might say simply edit the pizza to make it more healthy, which might confuse the most nowadays editing models. but we can simply use the LMMs to paraphrase it to, for example, adding some vegetables on top of the pizza, which can later bring us a better edited image. And similarly, we can use the world knowledge in LMMs to help understand what will happen if there is a hole in the blue, as well as what will happen after the 60 years. Furthermore, in addition to have LMMs help generation reasoning or expand the prompt in a single round, there has also been study trying to target for more ambitious iterative loops that use the LMMs to reasoning and help the generation. For example, now we can have those kind of in-context example. All of those are sent into as a single image that we try to extract the style from the stock image, apply on the top. And so the next image should also be the similar style, but apply on this top right person waving hands image. So this is done by simply repurposing V or other LMMs into multiple rows in, for example, how to improve the prompts, select multiple generated results, as well as providing feedbacks. So when putting together, such a system leads to several new scenarios in visual generation. So the first is that now the input not only needs to be a detailed image description, but it can be a very abstracted instruction. For example, we can simply say, help me design a hotel logo, and the LMM will propose some effective design and later convert them into image. And also, it helps extend the text image into the multimodal image and the text image, text input. So the highlight here is that instead of the image plus text input we've seen in some of the previous models, here we can actually just extract the arbitrary visual concept from our input reference image. This can be the tennis pose of this person, or the specific hat he's wearing, or the art style, or other arbitrary information related to the input reference visual image. And finally, in general, because of the feedback loop, it brings image of better visual and semantic quality. For example, the correct person count and the syntax spelling. So that's mostly on the LMMs helps generation, but to date, still mostly designed in a modular or so-called agent system design. Researchers are also curious whether we can have a more closer unification, bring into a unified text and image generation and the reasoning systems. So the very initial challenge is the format unification, that text is discrete tokens and the image is a continuous signals. So there has been some effective solutions. For example, showing the first part, we can have image quantized using VCO-GAN into a set of image tokens following the image autoregressive generation so that everything is a token prediction. We can also have an autoregressive text decoder, for example, one of our large language models, to not only predict tokens, but also some continuous features, which can later be sent into the diffusion decoder to bring us generated images. And finally, there has also been study exploring the possibility of having everything generated in the diffusion space. So all of those are showing some initial success in generating reasonable content. However, we argue that sort of the going beyond the initial challenge of format and modeling unification, the more important or remaining question is how to actually approach our grand vision of having such multimodal learning mutually benefit each other so that the image generation objective can help understanding and vice versa. And actually, there has been some recent study discuss this, why this might not be the case. So to my knowledge, this is still an open question. And a deeper question under this is that in order to achieve that, do we need a perfect image or pixel prediction in order to benefit the LMM learning, or certain type of abstracted visual representation is works better in these scenarios? And finally, towards the other direction of having the generative foundation model help understanding tasks. So the motivation is also quite intuitive, that the generation models can now generate good images following the world prior, for example, the human geometry and many other aspects. So it should contain some information that is helpful to understand the visual content. And how can we extract it or how can we repurpose the diffusion model to perform understanding tasks? So first is about first work is about how to extract representations. So one effective approach is to add certain amount of noise to the image that we try to denoise, and having the diffusion model run another network forward to try to denoise this noisy image and extract the corresponding intermediate feature as its image representation. For other more specific tasks, for example, image classification, there are also effective ways to simply directly repurpose the diffusion model to perform those tasks. For example, for classification, we will have a set of class labels, and we can simply add a certain amount of noise again to the image, and having the model do a denoising condition on all possible class labels. And for each class, we have a denoised image, and we compute which denoised image is the best one and select the corresponding condition as the final classification output. And the latest study also showed that if we further fine-tune following this classification pipeline, it can further improve the performance. And for depth and other dense prediction tasks that involves a 2D condensed map output, we can also do it by simply expanding the input channel, similar to an editing model, where the 3 channels are our original image that are always clean and used as the condition, and the other edit starting from the pure noise are generally trained to generate into a depth map or other dense output condition on this concatenated clean image channel. This turns out to be quite effective for depth estimation as well as for other related tasks. However, so here, the sort of status quo is that we have already observed some promising results on the dense output understanding tasks, for example, depth estimation, semantic correspondence, and so on. However, there has been some discussion on when trying to extract the global features from the diffusion model, it is not as quite effective compared with other popular choices like the one learned with contrastive learning also or self-supervised learning, as mentioned earlier in Zhengyuan's session. So in order to close this gap, there needs to be some additional steps we need to take to actually make diffusion directly effective as a vision encoder. So that's about the end of my sharing. So as a very quick summary, we talk about related topics for training about the image generative foundation models. We start with the training about on the pre-training side, the data, that's the importance of recaption, the effective DIT architecture, and the flow matching as well as VLR training paradigm that jointly leads to a more capable pre-trained diffusion model. Pre-trained generation model. We also talk about other improvements such as the inference time acceleration, as well as the post-training for human alignment that bring us a more effective generative foundation models. And also, we discussed the initial success and the open problems in combining generative foundation models with large multimodal models to achieve stronger intelligence. And also, the generative foundation model is actively shifting from image to more challenging modalities such as video and 3D, which Kevin will cover in the next session. So that's the end of my sharing. Thank you.